and we can begin. You can start sharing your slides whenever you want. I'll leave it up to you guys.
Okay. So Tommy, when I'm done, I don't need to do anything except just mute the camera and go without the video.
Yeah. Well,
he has everything.
Exactly.
Okay.
I'll end up mute. You can mute yourself, and but I can put you on. Just mute yourself, stop your video, and then we'll have Debbie work on it. So we're ready to go.
Okay. Well, I want to welcome everyone to our Lehigh NHERI seminar series. My name's James Rickles. I'm the principal investigator of the Lehigh multi-directional real-time hybrid simulation facility. This is a facility sponsored by the National Science Foundation. We're part of the community of the NHERI experimental facilities. And as I mentioned, we're sponsored by the National Science Foundation. Now, this is one of several seminars that we'll have this year. The purpose of the lecture series, if you wish, is to create a forum for researchers to present some of the latest research and findings in natural hazards engineering, of which our facility readily creates opportunities for researchers to conduct research at, including experiments as well as computational work. And so what I'd like to do today is then to welcome our speaker, Davide Gorini. Hopefully I didn't mispronounce your last name there, David. I apologize if I did. Let me give you a little bit of a background, and then I'll name the title here. But the background of our speaker is he's currently a postdoctoral researcher at the University of Rome. And that's the same institution that he received his PhD in an area of specialty is geotech engineering, but I know it does a lot in structural engineering as well. And so he actually has a dual doctorate, I guess, structural and geotechnical engineering. Sorry, I got to clear something here, apologize. So his research covers many areas, but his research in his dissertation was on soil abutment, macro element, sorry, not micro, but macro element representations for seismic assessment of bridges. So we're interested in the transportation infrastructure. Currently, he's involved quite a bit with the international community and creating opportunities. I don't want to say privileges, but really opportunities for open source numerical environments. So he's helping create that for sharing knowledge within the barriers. And that's really part of the mission also of the NHERI network. That's very important. And some examples are open seas as well as other supercomputing resources. And maybe at the end of this seminar, maybe you can maybe make reference to some of those other resources. Now, his current main research concerns include the development of thermodynamic, inertial, macro element approach to soil structure interaction, the seismic performance of bridges, buildings and tunnels as well, and particularly interested in computational tools for soil structure interaction applications in open seas, and the analysis and design of dissipative foundations and seismic protection solutions. And finally, very important is the geoconstitutive models for geomaterials and seismic assessment of natural slopes. So the presentation is entitled Controlling Inertia in Soil Structure Interaction. So with that, I want to welcome the speaker there and give you the podium there, David. Yeah, and thank you very much for presenting today.
Okay, thank you very much, Professor Rickles. Can you see my screen?
Yep, we can see.
Okay, just let me just set the pointer. Okay, good morning, everybody, and thank Professor Rickles for the kind introduction and for having me today. It's a great honor, really. Following up with the fruitful conversations with Professor Rickles about the relationship between the seismic performance of anti-seismic devices and substructure interaction, today I'm going to talk about controlling the inertial wall system by exploiting substructure interaction. And so let's first look at, just let me, because better. Okay, sorry. Let's first focus on the scale of the phenomenon we are dealing with, because we are here and know very well that seismic waves travel a long way before reaching us. And in addition to the side effects related to the propagation of seismic waves in the far field, so in the solar region not affected by the presence of the superstructure, the foundation inward motion per thermic structure is further modified by the direct interaction of the structure with a so-called significant soil region or near field soil region. That is not to be confused with near field earthquakes, having instead a short source to site distance. So soil structure interaction effects localize in this region and are due to the exchange of basically of inertial effects, inertial forces between structure and near field soil region, and to their different mechanical properties. So I will call this system the foundation near field system, geotechnical system from here onwards, or simply geosystem, that will be manipulated and analyzed today in order to mitigate earthquake-induced effects on some common structural typologies, such as girder bridges, buildings, frequency-based anti-seismic devices, and so on. So the sunrise in the background is due to the fact that the seminar aims at providing some openings towards the same solutions in which the soil is regarded as a cardinal component to control structural vibration. And to this end, I first need to introduce some numerical methods able to account for the distinct features of structural interaction in the nonlinear dynamic analysis of structures, for then controlling them in the second part of the seminar. And therefore, to this end, I will, in the second part of the seminar, I will introduce the concept of seismic resistance to structure system, providing some passive seismic protection solutions strongly interacting with soil. And that will be faced exactly by using the discussed numerical methods. So let's first, let's go through the first part. I see three levels of knowledge of problem: understanding, design, and assessment. Understanding complex phenomena typically entails a refined, specific, let's say, detailed analysis of specific problems, while design has completely different requirements, because it is definitely, and let me say fortunately, based on analytical or robust simplified numerical procedures in order to get very reliable and manageable results. Assessment can be associated with an advanced verification stage of structures. And from the standpoint of numerical modeling, it's more or less in the middle between the former goals. So the analysis approaches related to these goals will be used in a complementary manner in this seminar. And I will start to employ an advanced numerical modeling, an advanced modeling technique to point out the importance of soil inertia on the structural performance as important additional effects to the one developing in the superstructure that are instead, in my view, most well known in the literature, at least with respect to the soil effects. This is a reference example of the so-called direct approach that entails the use of nonlinear dynamic analysis on the whole soil structure system, simulating in a unified fashion the propagation of seismic waves. Hence, structure interaction effects are implicitly taken into account in the computation. This full soil bridge model was implemented in OpenSeas during my PhD and is inspired by the case study of the Pantano Viaduct that would be the approaching structure to the Messina Strait suspension bridge in Italy. So the structural model is very simple. It's composed of a continuous deck presenting an alternating strong and weak contact with vertical elements. And with strong contact, I mean that the deck is connected also longitudinally to the vertical support and not only in the transverse direction. The subsoil is composed of a dry deposit of the well-known Messina gravels, and the sole longitudinal component of a near collapse earthquake is applied to the base nodes of the soil domain. So the nonlinear dynamic analysis on such a system was carried out using the OpenSeas interpreter for parallel computing and using the supercomputing resources at the design safe facility in order to get reasonable computation times. Since the focus is for the moment on the solar inertia only, the structural behavior is regarded as a simple viscoelastic behavior, while the soil behavior is modeled through the PDNY model that is formulated within the context of multi-surface plasticity with kinematic hardening and non-associative flow. So the hardening response starts from the innermost yield surface until the attainment of the outermost ultimate surface, corresponding to critical state conditions for the soil. The model was calibrated on several experimental data on undisturbed samples of Messina gravels. And as an example over here, you can see the response to an undrained cyclic triaxial test. This is the relationship between the deviatoric stress as a function of the mean effective stress. And this is the evolution of the pore water pressure buildup with the axial strain. So let's come to the performance of the bridge. Expresses in terms of time evolution of the longitudinal displacements of the abutments and the strong pier, and the relative acceleration response spectra, and the post-earthquake deformed shape of the bridge. Well, the dynamic response of this case study of the bridge is going to be controlled by the response of the strong abutment. In fact, the dynamic amplification of the structure localizes in this spectral region, in which the spectra of the strong abutment and the strong pier show the maximum ordinates. And this can be ascribed to the resonance of the solar abutment system according to a first mode shape. In fact, the spectra of the strong and weak abutments are basically overlapped over here, and therefore this amplification cannot be related to the dynamic effects transferred by the superstructure. Amplification that engages in turn the nonlinear soil behavior, causing significant irreversible displacements and reflecting in permanent internal forces in the structural members. So soil inertia is driving the bridge response. And these peculiar features can be quite well captured by a direct approach, which, however, presents some drawbacks. Let's say, not drawback, maybe some complexities, because in addition to the computational effort that nowadays can be handled to some extent, but it also requires a non-trivial implementation of the model and interpretation of the results that make, in my view, this approach practical and feasible for design purposes, for which instead my standpoint to include soil structure interaction in the nonlinear dynamic analysis of structure is the macro element approach. Well, to date, it's been mainly developed for shallow foundations and oftentimes neglecting the soil inertia, while here a wider class of macroelements is proposed, conceived to simulate the nonlinear and inertial multi-axial response of geotechnical systems in the structural analysis at a minimal computational effort, because the macroelements are implemented in OpenSeas as multi-axial materials that can be assigned to a new zero-length finite element connecting to overlap nodes that can be connected to the generic base node of the global structure model. The generic macroelement that is called TEAM, thermodynamic inertial macroelement, reproduces the behavior of the foundation structure and of the near field soil region, and under dynamic loading is perturbed by a free field ground motion to carry out a nonlinear dynamic analysis in the time domain on the global structural model. A TEAM is a relationship between the generalized forces acting at the soil structure contact node and the corresponding capital Q sub I, and the corresponding displacements and rotations, small q sub j. Without going through the mathematical details, the teams are formulated as multi-axial, multi-surface, plasticity models with kinematic hardening, and derived within a rigorous thermodynamic approach typically called hyperplasticity, so that the incremental response can be obtained by simply differentiating two consistent potentials that are the energy and dissipation function. The yield surfaces of a team constitute the so-called plastic domain, within which the model exhibits an elastic plastic response, while the inertial effects developing under dynamic loading are reproduced through appropriate participating masses. So teams can exhibit a combined nonlinear and frequency-dependent response. Three are the basic ingredients for their calibration: ultimate capacity surface, initial stiffness matrix, and participating masses of the soil foundation system. As per the ultimate capacity surface, this corresponds to the load combinations activating global plastic mechanism of the geotechnical system. And in the team approach, so in a team, represents the outermost yield surface of the plastic domain. Yield surfaces that are assumed to be homothetic to each other and limiting the representation to the longitudinal and vertical space of the loads transferred by the superstructure. These are the initial configurations of the yield surfaces for the team for bridge abutments and pile foundations. Surfaces that evolve in the force space according to a consistent kinematic hardening law. So the surfaces present an increase in size from the first yield to the ultimate locus, so the ultimate capacity surface that can be calibrated. Actually, I mean to say that this can be calibrated straightforwardly according to based using let's say standardized procedures. So the surfaces present an increase in size from the innermost first yield surface enclosing the elastic response up to the ultimate surface. And for bridge abutments, this is the ultimate surface is represented by a rototranslated hyperellipsoid in the 6-dimensional force moment space of the forces exchanged between abutment and deck. While for pile foundations is a hyperegg with superelliptical generatrices, reflecting the importance of the load direction on the strength and stiffness properties of the geotechnical systems. Now, frequency dependence. It relates to the mass involved in the dynamic response. And using the team approach, this can be simulated by assigning to the generic soil structure contact node masses, M sub I, that are evaluated together with the initial stiffness metrics of the macro element in order to reproduce the dynamic amplification in correspondence of the resonant features of the geotechnical system. For bridge abutments, the model periods and masses along the several degrees of freedom of the geotechnical system can be computed through analytical solutions. And then the initial stiffness matrix of the team can be obtained by simply by the equation of the vibration period of a single degree of freedom system for each degree of freedom of the soil structure contact. For pile foundations, the participating masses can be taken as function of the small strain, the respective small strain vibration period, and initial stiffness matrix, quantities that can be straightforwardly obtained, for example, using the software developed by Professor Davide. Inertia models the cyclic response. I mean, let's for instance, carry out a series of dynamic analysis on this coupled soil abutment model and on the respective team. And by applying to the front wall in the former case and to the free node in the latter case, a longitudinal load varying over time with a sinusoidal law and varying the period. And this is the resulting dynamic amplification curve at small deformation levels that is quite well captured by the team, in which the maximum displacement of the abutment top normalized with respect to that produced by a static force is plotted as a function of the period. Well, the response is dominated by the first mode that occurs at a relatively large period, 0.6 seconds, because of the important inertial effects coming from the embankment mainly. And this corresponds to a much more open force deformation cycle with respect to that produced by a static application of the load in cyan. Moreover, in the nonlinear regime, the masses of the team interact with activated plastic flows and therefore interact with a reduced tangent stiffness of the model, elongating the natural period, as it is evident looking at the dynamic amplification curves for an increasing level, amplitude, of the load, where this is the small strain vibration period, while 0.8 seconds is the vibration period, the fundamental vibration period in the longitudinal direction for this system at large strain levels. A comprehensive validation of the teams is reported in the relative papers, while now I'm going to use this approach for predicting the dynamic response of some peculiar structural topologies. And by virtue of their computational efficiency, teams can be used for several purposes, from the analysis of the single soil structure system to extensive studies, for instance, aimed at pointing out critical issues in the current design methodologies. That is exactly the case of a large research project recently funded by Italian Civil Protection, concerning the seismic reliability of Italian code-conforming bridges, in which I was involved and had the opportunity to work with several people with different backgrounds. So the team approach was used to model structural interaction in the nonlinear dynamic analysis on a variety of soil bridge layouts, and the models were all implemented in OpenSeas. So 4 structural typologies was considered with reference to 3 sites with high, medium, and low seismicity. A multiple stripe analysis was carried out, considering 10 seismic intensities and 20 natural records for each. So the goal of the next couple of slides is to point out critical mechanisms affecting typical structural layouts in order to control them in the second part of the seminar. For brevity, I'm going to focus only on the case of the tall viaduct in L'Aquila, so in the high seismicity L'Aquila region, subjected to the selected 200 seismic records. The bridge rests on 5 supports, having deep foundations, and the soil presents a shear wave velocity varying from 200 meters over second at the foundational abutment A1 up to 1,000 meters over second in correspondence of the bedrock, located at 95 meters of depth. So, as per the static scheme, so the deck is connected longitudinally to PRP2 and 3, while to abutment A2 through a couple of viscous dampers, while it's free at P1 and A1. In the transverse direction, the deck is connected to all supports. Now, the teams for the abutments and the piers foundations were calibrated using the respective procedures just discussed. The piers are modeled as fiber section beam column elements reproducing the effective properties of the reinforced concrete cross sections. The bearings are modeled as the assembly, a proper assembly of rheological elements, and finally the deck is regarded as equivalent linear beam elements. A staged analysis procedure, I'm sorry, I missed to say that the soil friction angle ranges between 24 and 26 degrees. A staged analysis procedure was adopted, in which after the gravity analysis, the 3 components seismic motion is applied to the base nodes of the macro elements. Now, and the performance is quantified in terms of a concise indicator, the demand over capacity ratio, D over C, computed for all the devices and all the geotechnical systems along the 3 coordinate directions of the bridge. On the abscissa axis, we can see the 10 seismic intensities, while on the columns, we can see the support from abutment A1 to abutment A2 of the tall viaduct. Let's refer to the most severe performance level, that for the bearings consists in the uplift of the bearing in the vertical direction and in the attainment of the maximum stroke and of the shear resistance of the bearing in the horizontal direction, depending on the type of bearing we are talking about. And for geotechnical systems, the severe damage consists in the failure of the foundation piles. These are the computation times of the set of analysis carried out using the bridge model with teams. So the computation times are very low and don't require any partition of the model, nor the use of particular computing resources. Looking at the results, critical mechanism occurs starting from stripe, let's say 5, so as an intensity level equal to 5. That is lower to stripe 7, referring instead to, that is basically the design seismic intensity for the ultimate limit state. And this is mainly because of the inertial forces coming, in this case, from the abutments, from the embankment of the abutment, sorry. So critical mechanisms that are represented by mainly by the attainment of the capacity in the horizontal and vertical direction for the bearings of the abutments and PRP1, and in the failure of the foundation piles, mainly in correspondence of the abutments, exactly for that reason. So exactly for the soil inertia pushing the abutment inwards. Now, this result, in my view, shows something relevant, because the dynamic performance of structural system affected by soil tends to be controlled by a delicate arm wrestling between inertia and dissipation. Inertia amplifies the dynamic response in correspondence of the resonant frequencies of the whole system. This facilitates strength mobilization, also in systems that are typically regarded as linear in design and assessment, such as the case of abutments. But these critical features can be also regarded as a resource for a system, because it's well known that the strength mobilization, so the attainment of the strength, limits the forces that can be transferred to the superstructure. And this leads to the cardinal question pursued in this seminar. That is, how can structural inertia be controlled? Well, to this end, let me first introduce the concept of seismic resistance to structure system. I mean, a system able to balance its, let's say, intrinsic and added features towards the satisfaction of design requirements. And to reach this balance, I'm going to limit inertia in the overall system by weakening the geotechnical system, or I'm going to tune properly the dynamic response of the geotechnical system to the one of the superstructure. Of course, by considering the intrinsic features of the foundation soils that we have just seen that can play a role, but in some cases, this may be not enough. So we may need something more. I mean, the structural layout can be equipped with additional dissipative sources placed at the foundation levels or within the structural layout. And in many cases, these technologies interact profoundly with soil. Let me start closer to soil, talking about a mitigation technique whose performance is strongly related to the mechanical properties of the foundation. I'm talking about friction dissipative foundations. Well, some years ago, we were impressed, Professor Luigi Callisto and I, we were impressed by the adoption of this solution to the case of the Rion-Antirion cable-stayed bridge in Greece, and then in the Izmit Bay suspension bridge in Turkey, where the foundations of the tower were provided with an easily implemented solution consisting of a group of piles that are not connected with the overlying caisson, because of the interposition of a gravel layer between them, allowing for a controlled displacement of the caisson with respect to the foundation piles under strong shaking, dissipating energy by friction, and therefore limiting the maximum shear forces that can be transferred to the tower. Our focus was at first on the foundations of the Izmit Bay Bridge only, employing a very advanced numerical modeling that I don't want to dwell on, actually, because from that understanding, a simplified interpretative model was devised for a direct application in design. In the method, the foundation input motion comes from a ground response analysis and is applied to the base of a modified Newmark model that is composed of a rigid block representing the foundation combined with 3 single degrees of freedom system, providing a very basic description of the dynamic response to the superstructure. The dissipative contact between the foundation and the base exhibits a rigid, perfectly plastic, friction-based behavior. So for this system, the critical acceleration, that is the acceleration of the base motion producing the attainment of the shear resistance, so the relative sliding between foundation and base, is a function of time, and is definitely, of course, a function of the strength properties of the interface. This is the friction angle of the interface, but also depends on the foundation mass, on the vertical motion, on the inertial effects developing in the superstructure, and on additional water pressures acting on the footing, for instance, in the case of submerged foundations. So, in order to get a more general view to the factors controlling this quite complex performance of the friction foundation, an extensive study was carried out using simple Ricker wavelets as input motion, so characterized by an amplitude and a period. I'm going to discuss some results, just a couple of results of the study, in which, for simplicity, the seismic motion is composed of the longitudinal component of the base motion. So over here, you can see the relationship between the maximum relative displacements between the foundation and the underlying soil expressed in a non-dimensional form, as a function of the interaction parameter XIR, that is intended as the ratio between the fundamental vibration period of the superstructure to the mean period of the input motion. Note that other descriptors of the effectiveness of the friction interface can be equivalently used. For instance, the reduction of the maximum spectral accelerations in the foundation with respect to the input one. So this quantity takes more in general the name of generalized output quantity. These trends refer to a decreasing value of the mass participation factor of the superstructure HCl. So it can be noticed that the performance of the foundation is strongly affected by the interaction parameter, that because of the inertial effects developing in the superstructure, that in this region of maximum effectiveness of the friction foundation agree with the inertial forces developing in the foundation. This result, together with the other abacuses obtained as study, can be used for a preliminary design of the foundation. The objective is to limit the maximum shear forces transferred to the superstructure. So, given a structure in a specific site, a design requirement can specify that the maximum spectral acceleration, let's say max, be lower than a limit value, than a threshold, SA lim. Accordingly, the target generalized output quantity, Y sub I lim, can be computed as SA max minus SA lim normalized with respect to SA max. So the design consists in determining the optimum values for the interface shear strength and mass of the foundation, producing the desired generalized output quantity. This abacus relates the interaction parameter. To this end, this abacus relates the interaction parameter corresponding to the maximum effectiveness of the foundation to the relative excited mass. This is basically an indicator of the relative contribution of the inertial forces developing in the superstructure and those in the foundation to the overall dynamic response. So the results are quite well approximated by a bilinear trend. This means that given XIR for the case at hand, the foundation mass can be computed. And finally, through this abacus, one can obtain the shear resistance along the distributive interface by considering the target generalized response quantity, assuming a structural damping, and using the optimum value of the relative excited mass found before. So this simple design procedure is pointing out that the optimum performance is strongly related to the inertial features of the entire soil foundation superstructure system. But why not extend this simple, easily implemented solution to the case of bridge abutments, to the case of the problematic bridge abutments, exactly to control soil inertia transfer to a deck? Well, in this direction, let's make a first step that is very simple. So let's consider as a first case study an abutment with shallow foundation. And this is the corresponding capacity surface in the space of the longitudinal and vertical loads applied on top of the front wall. So the capacity is enhanced by the presence of loads pushing the abutment towards the backfill. But this capacity is not strictly needed under seismic loading, under static conditions. So it may be reduced in order to enhance energy dissipation under dynamic conditions. For instance, by embedding distributive interfaces within the soil, for instance, according to this arrangement, and using a friction angle of the distributive interface that is sufficiently lower than that of the soil. And this is the resulting ultimate capacity locus. So the capacity is reducing a lot along these load paths. In fact, the outer yield surface, distributive surface, is involved in a mechanism for load ratios equal or greater than 3, while the interface closer to the wall is involved for longitudinal loads that are proportionally larger. This abutment is exactly the one of the full soil bridge model shown at the beginning. So let's try to test this solution on this case study, but by using the team approach to model structure interaction in the structural analysis, and referring to the same seismic input shown at the beginning. In this case, the team for the abutments was calibrated considering the same initial stiffness of the basic layout, and the plastic domain calibrated on the new capacity surface locus, and finally the participating mass of the soil abutment system is computed as this volume over here, while this inclined boundary follows the outer distributive interface. Now, the performance of the bridge is quantified in terms of the time evolution of the relative displacements between the strong abutment and the strong pier that are the only elements connected longitudinally to the deck, and as evolutions, time evolutions of the flexural forces at the base of the strong pier. This is the shear, this is the bending moment. Consider the performance of the bridge in the basic layout, so without dissipative interfaces, in blue. Well, marked irreversible relative displacements develop in the deck during the interval of maximum intensity of the seismic motion, reflecting in important permanent internal forces at the base of the strong pier. This is because the strong abutment is driving the bridge response with accumulation of important irreversible displacements inwards. But if structural inertia is controlled, the performance improves remarkably. In fact, both the permanent and the maximum internal forces in the entire bridge layout reduce a lot. And this is due to the combined effect of the attainment of the strength along the dissipative interfaces and of the lower, much lower soil volume involved in the dynamic response of the bridge. And look that if in principle we were able to fully inhibit soil inertia at the bottom locations, this would be the result in violet. So leading to the minimization of the earthquake-induced effects in the entire layout. Now, let's apply this promising solution to the next case study that refers to abutments with deep foundations. So the bridge performance is again analyzed using the team approach. So the point is to calibrate the teams for abutments and the pier foundations, considering the presence of dissipative layers within the soil. Starting with abutments, this is the conventional layout of the generic abutment A1, but identical considerations can apply to abutment A2. And this is the capacity locus of the conventional layout in the space of the longitudinal and vertical loads applied on top of the front wall. In this case, I'm using a a slightly different, actually, layout of the dissipative layers, because this is aimed, as done before, to limit the inertia coming from the soil transferred to the superstructure. But in this case, in addition, in order to limit the horizontal capacity of the abutment, the piles are disconnected from the raft, again using a friction angle that is sufficiently lower than that of the soil. And this is the resulting ultimate locus. So the capacity is reducing a lot. As per the foundations of the piers, this is the layout of the pier P2, and this is the resulting ultimate locus, ultimate capacity locus in the usual space of the longitudinal and vertical load acting on the footing. And so in this case, the inertial control layout is exactly equal to the one of the East Bay Bridge foundations. So it implies the disconnection of the raft from the foundation piles, in which this value of the friction angle of the dissipative interface was found using the optimized procedure discussed before. So in calibrating the team, both the initial stiffness matrix and the participating masses of the soil foundation system were taken equal to that of the conventional layout, while the ultimate capacity was computed through the numerical procedure called DIP4, recently developed, that can compute the multi-axial failure loads of pile groups. So this is the resulting failure locus, and this means that the inertial control layout has the same compressive bearing capacity of the conventional layout, but a null tensile bearing capacity, leading to a much lower combined failure load on the multi-axial loading. Well, the bridge with teams was subjected to a three-component seismic motion representative of a strong shaking with a return period of 10,000 years. And over here, you can see the force deformation cycles in the geotechnical systems in the longitudinal direction and transverse direction for all supports from abutment A1 and abutment A2, while only for the Pierce foundation, over here you can look at the moment rotation relationship in the direction of the plane. Well, compared to the standard layout, the inertia control abutment A1 undergoes much lower irreversible displacements inwards, despite the attainment of a reduced active resistance, and also despite the attainment of the passive resistance in sometimes. These reflect also in reduced transfer displacements that are caused by the mobilization of the nonlinear behavior along a multi-axial deformation mode. This improvement in the performance is less evident actually for abutment A2 because of its connection with the deck through a couple of viscous dampers that limit irreversible deformations. Irreversible deformations that instead increase for the Pierce foundations because differently from abutments, in this case, we are not changing the inertia of the system, but we are reducing a lot its capacity. And if we look at the shear force drift cycles of the bearing devices in the longitudinal and transverse direction, we can notice that this reduction of the inertial forces transferred by the geosystems imply a noticeably reduction in the displacement moments for the bearings. So, playing with the inertia and dissipation can make the difference. Promising results that are encouraging us to further develop this methodology, especially towards the development of an optimized criteria for the selection of the friction angle along the dissipative interfaces of the inertia control abutments, and also to extend these solutions to different cases. While now, I would like to go through the last topic of the seminar. Because in my view, with respect to the previous developments, it's even less obvious that anti-seismic devices installed in the structural layout can be strongly affected by substruction interaction, such as in the case of frequency-based devices, but this is not the only typology sensitive to this issue. In this regard, I'm going to introduce a research path concerning the seismic assessment of tube mass dampers, in brief TMDs. Well, in its basic configuration, a TMD is made up of a very small mass compared to the mass of the superstructure and is connected through the ladder through a spring and a damper aimed at minimizing structural vibration. Optimal tuning of TMDs typically refer to a significant natural frequency of a structure with the properties of the TMD referred commonly in non-dimensional forms, calibrated in order to optimize the performance. So again, to minimize the vibration, the deformations of the structure. So most of the available design criteria refer to the simple linear to masses model, but several solutions demonstrated that such criteria are no longer optimal in the case, for instance, of a pronounced multimodal or nonlinear behavior of the structure, or because of the obvious fact that structures usually don't fly. Rather, soil foundation interaction can alter the deformation modes of the structural system, detuning the TMD response. And on the other hand, fortunately, the TMD effectiveness increases with its mass. That is typically assumed as an input in design, but is limited by practical needs. This is especially true for existing structures due to the limited available space. So, a possibility to overcome this limitation conceives the TMD as a super elevation of the existing layout connected to the ladder through a combination of bearings. Solution called the large mass ratio TMD because it allows us to reach a much greater mass of the TMD with respect to the existing structural layer. The sign of conventional or non-conventional TMD don't typically consider in a systematic manner substruction interactions. So first, I would like to use a refined modeling technique to point out the problem in order to understand the phenomenon for then trying to move forward. And this is the case study. So this is a coupled soil structure large mass ratio TMD model developed in open seas and describing the nonlinear and frequency dependent features of the system. So this is a typical existing 8-story reinforced concrete structure resting on shallow foundations and dating back to the 70s, so designed for vertical loads only. The structure, the super elevation is composed of 2 additional floors, reaching a mass of the TMD that is 20% the one of the existing structure. The structure is assumed to be located in the high seismicity Pantano region on the Messina Strait, and this is the profile of the shear wave velocity of the soil width depth. In order to limit the computation times of the analysis, the nonlinear dynamic analysis, the model was parallelized using OpenSysSP, and the analysis were carried out using the DAX supercomputing resources. The soil behavior was described by the PDNY model, calibrated as mentioned at the beginning, while the structural members were modeled as fiber section beam column elements, reproducing the geometry and nonlinear behavior of the cross sections. 8 spectrum-compatible seismic records were selected on stiff outcrop for each limit state considered, and the brown spectrum is the average one for a life safety limit state. Then, both horizontal components of the seismic motion are applied to the base nodes of the soil domain to carry out nonlinear time history analysis. Well, the TMD properties were determined using an optimum solution developed by the research group at the University of Salerno in Italy, neglecting substructure interaction and referring to the case of large mass ratio TMDs, which I don't want to dwell on for brevity. In order to vary easily its configuration, the TMD is simply modeled as masses placed at the top of the columns of the last floor and connected to the existing layout through a combination of elastomeric bearings and flat sliders calibrated in order to provide the design vibration period of the seismic resistance super elevation, whose performance is studied by considering or not the presence of the TMD and by comparing the results of the couple model with the ones in which substructure interaction is neglected, in which the foundation input motion comes from a ground response analysis. Here, the profiles of the horizontal maximum interstory drift, MID, for a life safety limit state scenario. So the MID increases upwards with a peak in correspondence of the width floor 7, in which the column cross sections become smaller. The TMD reduces sensibly, actually, significantly the MID, as it is also evident in the animated comparison, while soil structure interaction reduces moderately the TMD effectiveness, and especially in correspondence of the width floor amplifies the MID because of the deformation modes of the soil structure system. Now, in order to get a more general view of the problem, let's look at the dependence of the performance on the mass ratio of the TMD, where eta is the effectiveness of the TMD intended as the reduction of the maximum MID due to the presence of the TMD with respect to the case with no TMD. So the effectiveness increases quasi-linearly with the mass ratio, and the larger mass ratio, the lower the negative effect of substructure interaction, because these two lines are going to be overlapped for large values of the mass ratio. But what happens for a different intensity of the seismic motion? Well, when substructure interaction is neglected, dotted shadowed area, the effectiveness is moderately influenced by the seismic intensity, differently from what happens in the couple model, implying that substructure interaction is playing a crucial role in this game. In fact, when the seismic intensity leads to a marked plastic response to the foundation, so the effectiveness drops down, becoming even negative for strong shaking. The large mass of the TMD contrasts this detuning effect, and for a near collapse earthquake scenario, this is still a convenient solution for a sufficiently large mass ratio. So it is evident that the TMD performance can be strongly influenced by substructure interaction, and a large mass ratio of the TMD can contrast the tuning due to the nonlinear behavior of the node system and due to the couple deformation modes of the soil structure system. Now I'm going to show some next steps of this research concerning the development of an integrated design criterion for TMDs accounting for substructure interaction. But because of the huge number of investigations needed for this purpose, I'm going to first simplify the problem, eliminating all complexities that are not strictly needed. For instance, from this coupled nonlinear soil structure TMD model, we can refer to a linear planar structure equipped with a TMD and resting on an equivalent shallow foundation subjected to the sole horizontal component of the seismic motion, in which substructure interaction can be reproduced through the widely used dynamic impedance functions developed by Gazzetta's and co-workers, so simulating the translational and rotational frequency-dependent response to the foundation system. And if we assume that the structure deforms proportionally to its first mode, it reduces to a single degree of freedom system. Now, the model was formulated in a non-dimensional form using the Buckingham-Spy theorem, and on this basis, a simplified interpreted model was devised that is able to vary independently all the non-dimensional parameters of the model. The slope representing the superstructure is connected through the compliant base through a rigid link having a rotational inertia and a mass in order to account for a model height that can be different from the barycenter height of the structure system. So a global sensitivity analysis was carried out on this system as a series, a large amount, let's say, of dynamic analysis, considering a large variety of structural layouts and assuming that the TMD be designed according to the well-known DeNardo criterion. Because the focus was at first to point out critical issues in current design practice. The DeNardo criterion is one of the most widely used solutions, basic solutions in practice, for then trying to propose something new. So, as a result, over here, the effectiveness of the TMD associated with the model with compliant-based is plotted as function of the effectiveness of the TMD obtained with the model with fixed base, in which the effectiveness is in this case intended as the reduction of the maximum base shear forces in the superstructure. So structure interaction can even lead to a negative effectiveness of the TMD, but it's just in minor cases because almost half of the samples are located in region 2, in which the TMD effectiveness is partly reduced by substructure interaction, despite the device still provides a favorable effect. In fact, basically in this region, it's happening that the TMD response is partly detuned from the superstructure response because of combined translational rotational modes of the entire system. So the objective of the design criterion that we're developing is exactly to move as much as points as possible upwards towards region 1, in which the DeNardo solution is still the optimal. But to this end, I think that we need to know something more. So what are the factors dominating the reduction in the TMD effectiveness? Well, this information was obtained by using the elementary effect method by Morris to the results of the sensitivity analysis. And these are the resulting dominant parameters for the problem at hand. The figure shows the elementary effect associated with all parameters of the models with fixed base and deformable base. Basically, the elementary effect is an indicator of how much the model response is affected by that parameter. And when substructure interaction is considered, it can be inferred that the TMD performance is not only controlled by the usual structural damping and the TMD mass ratio, but also on some parameters, additional parameters. First, the structure to soil relative stiffness and parameters G7, 9, and 13 that are instead related to the rocking at the foundation level. Now, we are approaching the end scene of this story because we are now in the process of relating the parameters characterizing the soil structure layout to the ones associated with the TMD producing the optimal performance. For instance, if we look at the relationship between the TMD frequency ratio and the other circled factors over here as a first result, this is the corresponding result. Actually, this is not yet published, so feel free to contact us if you need more information about it in the meantime. So over here, the effectiveness of the TMD is plotted as a function of the frequency ratio of the TMD and of the structure to soil relative stiffness. For a given mass ratio, the optimum value of the frequency ratio is definitely a function of the relative stiffness between soil and structure. And this optimized solution can lead to a much more a much improved performance of the structure. In fact, over here we can see this is an indicator of the effectiveness of the whole system plotted as a function of the structure to soil relative stiffness, and this is the so-called TMD performance curve obtained with the basic Denartok solution for designing the TMD, while this is the optimized performance curve. So the performance is improving a lot because the red curve is moving upwards. Well, this is the end of this path through the meanders of structure interaction as a means for controlling structural vibration, in which we have talked about some numerical methods able to include distinct features of structure interaction in the nonlinear analysis of structures. So, and exactly using these methods, we pointed out some critical issues in current design methodologies, and we highlighted the importance of structural inertia in controlling the structural performance. And to control structural inertia, we discussed several solutions. Basically, two options were discussed. First of all, I can exploit the distributive features of the whole system, or I can tune properly dynamic response of the geotechnical system to the one of the superstructure in a convenient manner. And actually, in my view, this is a very fascinating path, because in order to reach the goal, we need to pass from conception to modeling, from modeling to design, where simplification and, let's say, idealization, identification, sorry, of the dominant factors of the response are fundamental for better guiding our idealization of reality towards effective solutions. And as a final remark, I would like to thank you and all people that I have the honor to work with in developing these challenges. Thank you very much.
Oh, sorry, David. That very interesting. I had to try to unmute my system. I can't get my camera to come back on. I'm not controlling it here.
No, it's fine.
So anyways, is there any questions from the audience that you may have for the speaker? Any questions at all? Tommy, can you put my camera back on, or I can't seem to be able to control it?
You're allowed to turn your camera back on. We currently don't have any questions from the audience right now. They could either raise their hand in Zoom by using the toolbar at the bottom, or ask questions in the Q&A section or chat section.
I had a couple of questions, David. They're very interesting, but I'll wait to see if anyone else, we try to engage the audience here. You're very active in publishing. It's very important, as you know, to get the word out, to communicate with people. I think this is very, very interesting here.
Let's say we enjoy the studies. I
think you pointed out, soil structure interaction is very important. Get help or get hurt, right? And
it can play a role. Absolutely, it can play a role.
Yeah, and when I took geotechnical engineering, foundation engineering as an undergraduate, the professor, and I think he was right, he said, when you're standing and you look under your 2 feet, the left foot could be under a different type of soil than the right foot. So there's a lot of uncertainty on top of
absolutely
everything else. Yes, I had a couple of questions there. You had the I'll just call it a transfer function, but that the transfer function was what, from the bedrock up to where the foundation was interfacing with the soil. When you had the macro elements, you ended up with it. I'll just call it a transfer function because the notation looks similar. So that the transfer
I'm not
function.
I'm not sure to get your point, Professor. So you're talking about the seismic input for the macro element or something else?
The macro element, yeah. I was curious about the macro elements there. So it's interfacing basically the waves originating at the bedrock. Do you have to do a deconvolution up to the interface? But the foundation, you go from the foundation down to the bedrock, the macro element, what does it represent?
Very good point, Professor. Absolutely. Yes, I missed to specify this point actually, because, the seismic input for the macro element derives from a separate analysis in which we simulate the propagation of seismic motion from the bedrock to an effective depth. That is basically that can be regarded as the lower boundary of the volume of soil interacting with the foundation. So this analysis, this separate analysis, is basically a site response analysis because it is related to the far field soil region, so to the region of soil that is not affected by the presence of destruction. And therefore, we can use several techniques for evaluate these so-called site effects. Then these site effects at the effective depth of the foundation can be directly applied to the macro element as translational motion. But if we are able to also identify the differential displacements occurring in proximity of foundation, we can also, in principle, be able to apply rotational components of the seismic motion.
Okay, that is very, very interesting here. Your multi-yield services remind me of morose hardening there. You know, it's what was the hardening rule you used to? I mean, those services, I assume when you engage the inner service, it should translate until you engage the outer service, and that defines the hardening. Yes. What kind of hardening is assumed there? Is it based on the distance between the centers of the circles and it's progressively decreasing, or is it by multifaceted linear? Because it's very similar to morose hardening.
Yes. So this is the beauty of hyperplasticity, because using hyperplasticity, the hardening law derives simply from the definition of the potentials. And in this manner, we are able to get an hardening law that is energetically compatible. So respectful of the first and second law of thermodynamics. And actually, in this case, we are looking at models that are with surfaces that cannot intersect with each other. So these are not nested, these are also called in some cases nested yield surfaces. This is a quite simple, actually, hardening law, because the surfaces follow the force state. We are talking about the macro scale, so follow the force state without intersecting each other.
Couple other questions. I'm very interested in what you do. We've done somewhat related work on that. On the bedrock, do you assume that bedrock, where the waves originate, is there any wave traveling, or is it a uniform motion across the whole basin where the bedrock is? Depending on the distance, it may be slightly different, right? The accelerations, or
absolutely, it depends on the cases, because in the case in which we know the depth of the bedrock, so in the cases discussed in the presentation, the seismic input was recorded on outcrop. And therefore, a deconvolution procedure was at first applied to transfer the motion from the outcrop to the bedrock. And then, through a site response analysis in the macro element approach, or through the nonlinear analysis on the full model in the direct approach, we are able to propagate the motion through the superficial soil deposit. The motion at bedrock, in any cases, was at least considered as the three translations, so three translational components. So at bedrock, I think that it's quite reasonable, because otherwise, there is also the possibility in a more modern fashion to model the rotational components of the ground motion. Now, when we need to refer to something different, for example, there is the DRM approach, the domain reduction method approach, by which we are able to also account for surface waves and so a different propagation, but this is something different.
Yeah, the last question I have is the boundaries. You know, you have a basin. Maybe you can go back to the first model. You have the basin, you have the bedrock, and you have the structure on top. So I know you have to be careful about the radiation damping and the wave propagation that doesn't get stuck in the basin, because in reality, I mean, it can propagate outwards. So I guess you have to take into account special consideration for the boundaries of your final element model if you were to take that approach, right? So the radiation damping, do you use any type of far field elements, or what do you recommend there? I mean, there's been different approaches that have been done. And sometimes they want very thick plane strain elements.
You're right, Professor. This is a tricky point in the conventional, as I say, conventional direct approach, because using the DRM method is different, is something better than the conventional approach. But using the direct approach, there are, as you said, different possibilities. In the cases that you saw before in the presentation, so I used at the base viscous dampers calibrated according to the Joyner-Chen procedure to account for energy dissipation and reflection of waves at the bottom. While laterally, I used both equal degree of freedom constraints, so a kinematic condition between nodes on opposite sides in order to enforce free field condition at the boundary. And this can be, let's say, this can be quite okay if the boundaries are in fact quite sufficiently far from the section. Otherwise, in other cases shown in the presentation, I also used dash pulls applied to the lateral boundaries. And in one case of the full model of my PhD, I also used the so-called free field columns. So that are soil columns surrounding laterally the soil domain and interacting with the inner soil domain through viscous dash pulls, calibrated, let's say, according to along the similar lines of the Joyner-Chen procedure. So several techniques, it depends on the case under examination, because of course, in my view, the best manner to model this aspect for using the conventional direct approach is the use of free field soil columns or in open seas, but not only in open seas. There is also another interesting possibility, that is a so-called perfect matched boundaries. That is another very good possibility that I can suggest.
Okay, yeah, thank you very much there. I don't know if there's any other questions from the audience, Tom.
We have a question from Boris. Boris, I'll open it up for you to talk. You can unmute yourself.
Yes, can you hear me?
Hello, Professor.
Hey, Davide. Hey, thank you very much. I just wanted to congratulate you on a great talk. I just sent you an email. James, we need more talks on soil structure interaction because this is really, really important. Anyway, thanks a lot. I just wanted to congratulate you. Thank you, guys. See you later.
Thank you, Professor.
Yeah, I was gonna mention to you that you know, that the soil is the foundation of everything. I mean,
exactly,
the buildings stand on it. Without the foundation and considering that things can't exist. So I think we have to create more of an awareness of that. You know, that sometimes I know people in the geotech field sometimes feel either slighted or concerned about that. And so what we've done in our facility is to try to engage more in the soil structure interaction. So I think your presentation is quite of interest to us, and we've talked a little bit with Boris, but look to collaborate more with the geotech community, because I think it's important to recognize the importance of the effects it can have as you demonstrated there.
Thank you, Professor. I agree.
Yeah, and the challenge is too that it's a quite big domain which you can't put in the laboratory to maybe try to
yes,
the structure. So the computational modeling or coupling with field experiments is very important.
That's not easy at all. And from the experimental point of view, there is also the other big problem about reproducing the effective stress state in the soil under static conditions, because we know very well that the seismic performance is strongly affected by the stress state before the application of the seismic event, but this is not this is not let's say straightforward in the experimental facilities because the soil stiffness and strength depends strongly on the stress on the stress state. So this is not easy to produce the in situ conditions.
Yeah, but Boris, did you have another question? Your hand is raised, or you're high-fiving.
Oh, I'm sorry. Okay, now I should.
No, it's okay.
I'm sorry. No, just wanted to thank you, and I think it's a great topic, and thank you for for bringing the topic of the dissipation of energy, because that one can gain a lot of benefits from taking soil into the account, and it just has to be done. And thank you again. Thanks.
Thank you.
No, yeah, thank you. And Boris, I was going to mention everyone, if you have an interest in presenting at our seminar series, I mean, Boris, you should think about this too. People are always welcome. If you just want to send us an abstract, as I say, we try to schedule a number of these for the purpose I stated. And I think this would be an opportunity, I think, to create a forum, particularly for the soil, the geotechnical field and the computational aspects that are important on that. Well, I guess, I don't know if there's any other questions, or I don't have control over the board.
No, that's all the questions we have right now. And I think, we're over 15 minutes, so I think we'll, start to wrap it up then.
Yeah. So David, I want to, thank you, and maybe others could join me in, really giving an applause there. I thought it was.
Thank you for giving me this opportunity. Thank you.
Really great, and we should stay in touch, because we're interested in what you're doing, as well as Boris and the others, and you're doing hybrid with soil structure interaction. I think there's a lot of potential to integrate the work that you guys are doing in the field to try to link the two domains there. So we'll definitely be in touch. I'll send you a follow-up email. And again, I wanted to thank you and taking the time to do this. Unfortunately, it took some time to get the logistics worked out because of the timing there, but I'm glad you were able to make it here, and wanted to thank you there. And I guess for the audience there, we archive our presentations. I guess you cleared that with Tommy, David, that we archive that and make it available.
Yes, this is all on the Design Safe page, the Lehigh Design Safe page, and the webinar recording will be up in a couple of days. I mean, for anyone that did not see it, we could pass along those links. David, for anyone that might be interested, we'll provide that link. So yes, it'll be archived and saved.
Yeah, so we get a lot of viewers on that, David, and we've had people cite actually their presentations. You use those for proposals as, say, citing work that they've done, so it's definitely citable there, and we'll have it readily available for anyone that wants to view it there.
Yeah, sure.
Okay, well, I'll look forward to touching base with you. And I think, Boris, the last time I saw you, I think was in China before the pandemic there. So hopefully I'll get to see you in the US.
Yes. And if I may note, today is the first day of the lockdown 3 years ago. So something to celebrate. I'm just joking. Never mind me.
Yeah. I don't know. I'm always worried about that. I go into class and, I'm not blaming the students, but you have a big circle, a big diameter, and people come together. They come from all different areas there. You always have to be a little bit cautious there. You don't really know this is a smart thing here. We have to be very careful, but if it's not one thing, it's another. So
yeah, exactly. You have to worry about something.
Yeah, you can't let it control you there. So anyways, I guess Tommy has control of it. So with that, we could conclude.
Thank you all, guys. Thank you. Bye.
All right, take care, everybody, and thanks for joining.
Thank you.
Yeah, and David, I'll be in touch. We're using Neural Network to do a lot of the things you've done.
Absolutely.
I really want to do some experiments with you where we've been using TMDs.
Professor, we discussed a lot about this. Yes, that would be very interesting. Yes,
I think that the timing is good. Tommy's been involved a lot, and we've actually had full buildings of isolation systems. And I keep telling people, you got to put the soil underneath because it changes the whole complexion. So we're doing the fixed base, and I think we should follow up with, if you're interested with having a soil underneath and modeling it. The challenge, as you know, David, is very fast computations are needed because the devices in the structure are rate dependent. And so what we've done currently we've trained neural networks to try to model the effects of the foundation, and we have friction and the overburn pressure, all that's accounted for. But I think we have we reduce it very significantly down to maybe 6 inputs, 6 outputs, but I think it could still go to the next level. And I think the results that we're finding is very astonishing there. In other words, we're just trying to show the methodology about how it could be done, but then I think we should start to working with it to show what the effects would be if you account for it. I think it will be quite informative. So we should think about planning on having maybe a Zoom. We could discuss some things. I think what I can do is make a short, brief presentation, show your status quo, and perhaps we can think of some interesting things. I know Tommy's quite involved in the IT side, and he can tell you.
It would be very interesting. It would be very interesting.
Computational part, but we're ready to work. Okay. So, anyways, it's taken some time. I should let you go, David. What time is it there? Around